Let me work out an example on how to check if a set is a subspace of a given vector space. For example, let V be the set of all the vectors that are of the following shape: x minus 3y, y, and 2x plus y, such that x and y are real numbers. And let's try to prove or show that V is a subspace of R3. V is a subspace of R3. For this, what we need to check is that our set satisfies two properties. One property is that the sum of two vectors, if V and U are in V, this implies then the sum is also an element of the vector space. And then two, if we have a scalar and we have a vector in V, then the scalar times the vector is also an element of the vector space. If we have that V satisfies these two properties, we have that V is a vector space, and since it is a subset of R3, it will become a subspace of R3. So let's start checking these two properties. The first one, let's grab two elements of our vector space, of our set. So let's say x and y be real numbers. That means that we have that a particular combination like this would be an element of our set. This is an element of our set. But we can also take other parameters, say x prime and y prime, and we have that those two will become parameters for particular vectors in our set. In here, what we did was we chose two sets of parameters that gave me two different vectors in our set V. And what we want to do, let's call the first one U and the second one V, is we want this to give me a combination of vectors that are inside of V. So we want to show that this is also part of that set. In other words, what we want to show is that if I add these two combinations, we end up with something else that is also in V. We want to show that that is also in V. And what it means to be in V, well, it means that we satisfy a shape like this. That means that we should be able to find two parameters such that the coordinates for that vector are on that form. So what it means is the following thing. If we add these two different vectors, remember this is V and this is U over here. If we add these two vectors, what we have is the following. We have x minus 3y plus x prime minus 3y prime, y plus y prime, and 2x plus y plus 2x prime plus y prime. Remember that in here we have just a single vector. This is not a matrix. This is a vector with three components. And what we're aiming for is to actually be able to write this singular vector following the original shape of all the vectors in V. If that's possible, that means that this is also an element of V. And we can actually do this. If we rearrange the parameters that we have, we can write them down in the following way. Minus 3y plus y prime. So just rearranging and putting the x's together and the y's together, we actually have this. The bottom one, we have y plus y prime. And then the last column, that would give me just something similar. 2x plus x prime plus y plus y prime. So in order to make sure that we see that this is actually of the required shape, I'm going to relabel the parameters. Let me call the parameter x plus x prime. Let me change that variable and call that s. And the parameter y plus y prime, let me call that t. So what we have in here is simply that I have s minus 3t. I have t in here and 2s plus t. Notice that this last part is exactly the same shape or the same blueprint that all the vectors in V have. Because if we go back into this, we have parameter minus 3 times parameter. That's my first component. And this one satisfies that, parameter minus 3 times parameter. The second component is the second parameter. And this also satisfies that. And then the last component is 2 times the first parameter plus the second parameter. And that also satisfies that. That is 2 times the first parameter plus the second parameter. So just by rearranging this, we now know that this is also a vector in V. In other words, what we just showed is that if I have the sum of two vectors in V, then that is also going to be a vector in V. So that's the first part. We already showed the first part of the properties of vector spaces. Now for the second part, we'll do something similar. Now let me grab two parameters. So I actually have, let me call it V, which will be x minus 3y, just as before, 2x plus y. This is an element of the set V. And let me also grab a real number. Here is very important that we make a difference of what is what. Since x, y, and c are real numbers and v, little v, is a vector and capital V is a set. So now what we want to show is what happens with c times v. We want to know what happens with this combination. What we need to see is if we can rewrite this vector following the same ideas as before and show that this is an element of V, of the set V. So what we have in here is that I can distribute this, and then we will have Cx minus 3 times Cy, Cy, and 2 times Cx plus Cy. And now I'll do a very similar trick as before. I'm going to relabel the parameters so I can see easier than the result is actually in that vector space. If I call S the multiplication of C and X and T the multiplication of C and Y, then that result can be written as S minus 3 times T, T, and 2S plus T. And just as before, that follows the pattern for being an element of V. Because again, we have that this same shape that we have in here is satisfied. We have first parameter minus first times the second parameter, and 2 times the first parameter plus the second parameter. This is exactly the same thing that we have over here. We have the first parameter minus 3 times the second parameter, the second parameter, and 2 times the first plus the second parameter. So that means that we have that both of our properties are satisfied on this set V. This means that V is a vector space. Hence, we have that V is a vector space. Remember that V is a set. This is a collection of vectors. And all those vectors form what we call a vector space. Now, this vector space lives inside of R3. And that we can see because all these vectors are three-dimensional vectors. They have three components. So what we can say is just a different way of saying things. We say that V is a subspace of R3. We have that V is a vector space on its own, but since it is a subset of R3, we call that thing a subspace of R3. We can also find out a basis for this, which means some vectors that will generate everything. And we can find out that just by following the shape of the space. We have that the set is generated by combinations of things that look like this. So we can separate this using the properties of a vector space. Because if I have a vector B in big V that is given by x minus 3y, y, and 2x plus y, then we can separate this as follows. We can write down all the x's and all the y's as two separate vectors. In other words, for example, we can write down this as x, 0, and 2x, and negative 3y, y, and y. Notice that the only thing that I did was to split this into two vectors, which we can do. Basically, we're doing just reverse engineering of this. And now the next step that I can do, I can not only add things, but I can also multiply by scalars. So I'm going to do the inverse of distributing a scalar. That means I can factor a scalar out. So I'll get 1, 0, and 2 plus y times negative 3, 1, and 1. Notice how if I start from this side, I can arrive to the previous one. So all I did was to basically reverse engineer this part. So now I can go from that part to the last one. This will tell me that I have two very good candidates for being the basis for this vector space. I have that these two will be two very good candidates for being bases. Because we see that everything in V is generated by a linear combination of these two vectors. So what I would have to show is that this is actually, well, it spans V. And I would have to show that the two of them are linearly independent. So hopefully you can see that the first part is met. Basically what I have up here is just a general linear combination of the two of them. So I indeed have that the span of these two vectors, the vector 1, 0, 2, and the vector negative 3, 1, 1, this is indeed the whole vector space V. So we have that first thing. Then the second thing that I want to show, that I need to show, is that these two vectors are linearly independent. And this one is also easy to see, because since I have just two vectors, in order to see if they're linearly independent or not, I would have to check if the secular equation has non-trivial solutions. Remember that in order to check if a set of vectors is linearly dependent or independent, I would ask for solutions of the secular equation. So if I try to work out this secular equation, what I would have is the following thing. I would get A 1, 0, 2 equals to negative B, negative 3, 1, 1. And I can write this down in coordinates, because that would mean that A should be equal to 3B, 0 should be equal to negative b, and 2a should be equal to negative b. So from here, we see that from the second equation, we have b equals 0. It has to be equal 0. And if I substitute that into the third equation, that also tells me that a has to be equal to 0. In other words, I only have trivial solutions. And this means that the set of vectors is linearly independent. If I only have trivial solutions, this is linearly independent. In other words, I can say that the basis for V, this set is a basis for B. And since I have two of them, we have also that the dimension of V, let me call it this way, is 2, which means the number of linearly independent vectors. I also want to say that this is the maximal number of linearly independent vectors. In other words, what we figured out was the following thing. We have our set V given by this particular pattern. We show that since it satisfies these two properties, it has to be a vector space. And since it is sitting inside of R3, we have that this is not only a vector space, but it's a subspace of R3. I also went ahead and tried to find a basis for this, which means try to find two vectors that will generate the whole thing. That means that they will span the vector space, and they also have to be linearly independent. So with all those considerations, we have that this has dimension 2.